Thank you for the introduction. My name is Paul and I'm from the Institute of Physical Materials in Brno, also as all my colleagues. And I will show a presentation about the description of the short fatigue crack propagation under low cycle fatigue. It means that there will be a big plasticity around the crack tip. As was postulated by Suresh and Shriki, there is a different area of the small cracks, and as you can see in this sketch, that the short cracks can propagate even in a higher fractal rate than the long cracks, and also on the threshold. And the main area of the short cracks can be defined here. So, as was presented here in previous presentation, the big area of the small cracks is really influenced by the microstructure unit, which then the cracks can propagate on the threshold, and some barriers in the microstructure can influence the short cracks. And the other thing, which is also the problem, is that the length of the small crack is compared in the scale of plasticity. So the small scale yielding condition is failed here, and this will be exactly the case of our study. And also, in our case, the cracks are more or less physically small in most cases. I will show the motivation first. That was our results which we obtained in the measurement of the Eurofer steel, that we trying to estimate the fatigue fractal rate of the really small cracks. The experiment was done in this type of specimen, where it was a small shallow notch in the middle, and using the long distance microscope, the fatigue fractal rate was measured. And when we plot the diagram, fatigue fractal rate against the stress intensity factor rate, we found that each applied strain have its own fatigue fractal rate curve, so it's impossible to predict fatigue crack propagation even for only different loading conditions, which it's not really useful. Also, when we compare this small crack behavior with the long cracks measurement on classical CP specimen, we obtain with all these features I shown before, that the small cracks propagate in a higher rate than was predicted by the long cracks, and also under threshold. Therefore, we start to study this behavior of the crack, and for the experimental use, we use this free type of the steels used in energetic industry. It's a 316 steel, Eurofer steel, and also Eurofer steel strengthened by the yttrium oxides, which means that the chemical composition of this ODS Eurofer steel is approximately similar as the chemical composition of the Eurofer steel, but there is additionally the small yttrium oxides dispersed in the steel, which really influence the strength of the steel. And we also use material already published. All these experiments was also done in our institute, and for comparison we used the aluminum alloy 6082 and 22.5 duplex steel. Here you can see the experimental specimen used for this experiment. So there was a cylindrical specimens usually for all these materials with a diameter about 8 millimeter. There was a shallow notch on this specimen to be sure that the crack will initiate in this area, which will be observed by a long-distance microscope. And only for this ODS Europe steel was developed the miniaturized specimen, and it was due to the really small amount of material available. And in this case, the diameter of the specimen about 2 millimeters. It was possible also due to a very fine microstructure of this material, because here you can see the EBSD of this material, and you can see that the most of the grains is under 5 micrometers. So even this prepared notch about 50 micrometers was 10 times bigger than the typical microstructure using of this material at least. So in these specimens, the fatigue crack or fatigue cracks was initiated naturally, only due to this shallow notch, and in this specimen, only in this one, was using focus ion beam technique, prepared small 3-notch, and the crack propagation was observed from this area. Here you can see the experimental procedure. So the cyclic test was performed on servo-electric testing machine at room temperature. Strain amplitude was kept constant during the measurement, and the fatigue test was regularly interrupted, and we can observe then the propagation of the crack. Here you can see the light micrographs obtained from ODS Europe steel. For example, here it's possible to see photos of 316 steel. So you can see that when you compare these two, that in this area was prepared that big 3 cracks, so the crack is propagated from here. In the other specimens, the crack was initiated naturally, so you can see that there is some network of the cracks, called the small cracks, and one crack starts to be bigger than the others and lead to the final damage of the specimen. So from all these experiments, we obtain dependence between the length of the crack and number of the cycles, and using the classical procedure, we can estimate the value of the stress intensity factor for these cracks, and plot the diagrams. And you can see that all these diagrams have the same problem, like that one in motivation, that with increase of the total strain amplitude, the fatigue crack growth rate increased. And that's because here, for these loading conditions, linear elasticity fail, and it's necessary to also include the plastic part of deformation in front of the crack tip. So we use the chain integral to describe behavior of these small cracks, and therefore it was necessary to do some Finite element modeling, we consider the semi-elliptical small cracks, and due to the symmetry of the problem, we model 1/4 of the specimen, and we estimated the value of the J integral for each material used in the study and for each loading conditions used in the study. So here you can see the cyclic stress strain curve for each material. So you can see that there is a big difference in the material behavior. The highest stress strain curve is corresponding to this Euroferrodia steel and for example, in comparison with the Eurofer steel, which have the same composition, but only yttrium oxide is here. So you can see that you obtain approximately twice cyclic yield stress, for example. So you can see that these materials are really different from each other. And we describe that fatigue correction rates for all materials using the J integral value. And you can see that it's better in comparison with E, but it's still not really perfect. There is still this dependence on total strain amplitude. Always the highest strain amplitude is really up, and there is a big scatter of the results. So be inspired, for example, of the Pollack model, which trying to describe the small fatigue crack behavior based on the plastic part of the strain. We used only the plastic part of the J integral to describe behavior of the small cracks. And you can see here that all these experimental results are collapsed to the approximately one line. We should also consider that in fact one line is correspond to the one experimental specimen, so there is still some scatter, there is can be still some differences. For example, here in 316 steel, there's one curve with different, but on this steel we are still measure this propagation also for the different amplitudes, so we will see the results. For this Eurofer steel, it's really close to the one curve. In this aluminium alloy, there is only for the different loading conditions, it perfectly fits these two curves together. There is only difference between the longitudinal transversal crack propagation for the specimens cut it from the rolled plate, so there is a different orientation of the microstructure a little bit. And also here is some scatter in duplex steel, which is also quite difficult material because there is a relatively big microstructure. But more or less all the data fit together. So finally I plot a graph where is the fatigue correction rate against the plastic part of the J integral. And at least we can say that it's possible to modify Paris law for these small cracks in really low cycle fatigue conditions where it's big plasticity around. That only the control variable is not the stress intensity factor, but the plastic part of the J integral. It's possible to describe these two material constants, which seems independent on the loading conditions. So each material can be described by this equation separately. In addition, when you see this graph where is all material together, you can see that the difference between the fatigue crack propagation of the small cracks in these really different materials, it's not that big. So we can say that in this graph there is some band of the crack propagation, of small crack propagation. Then using this average data, it's possible roughly estimate behavior of the small cracks in such kind of the metallic materials. So that's all. Thank you for attention.